Good morning. Thank you for the introduction. This morning I'm going to be talking about our preliminary work for our polycrystalline diamond circular resonators that showed a low onset of nonlinear response. So why diamond? For diamond, we want to look at it for harsh environment applications due to its chemical inertness, its mechanical durability, thermal stability, and biocompatibility. The biocompatibility is especially going to be an issue in the resonators that we will be looking at in the future after this work. The other advantage for the diamond membranes is that they can be doped for both N-type and P-type or insulating materials. This will allow us to create both the electronics and the resonant devices that we'll be looking at. Diamond also has a very high Young's modulus, which we are looking at for tuning our resonant devices. Previously, we have looked at resonators for their use in high accuracy sensors. Recent sensors have shown measurements for displacement in the range of femtometers, mass sensing in terms of zeptograms, force in the range of attonewtons, and energy at the range of attojoules. Diaphragm resonators have also been shown for use in pressure sensing, gas sensing, and for biomedical applications. Our previous work for silicon carbide, this is a polysilicon carbide resonator shown here. We've shown pressure sensing with multiple mode resonances with very high Q factors. Fabrication of these diamond membranes consists of a silicon substrate, then a Aztec's microwave plasma CVD system is used to deposit the diamond film on the silicon substrate to a nominal thickness of 100 nanometers. The diaphragm fabrication consists of a simple backside masking and a H&A edge for the bulk micromachining. The resultant membrane is circular and in this example, has a diameter of approximately 1.4 millimeters. This gives us an aspect ratio of area to thickness of approximately 15,000. We wanted to confirm that this material was nanocrystalline diamond, so we did Raman spectroscopy, and the spectrum, though it doesn't show the strong peak for regular diamond, has been shown to match nanocrystalline diamond under certain deposition parameters. We also ran AFM on the surface of the diaphragm and found that the surface roughness was approximately 4 nanometers and the crystal size was approximately 100 nanometers. Our resonant test setup consists of a helium neon laser with a beam expander, the standard interferometry setup with a 50-50 mirror, an objective lens, and our vacuum chamber where the sample is held. We have a electronically controlled XYZ stage with sub-micron accuracy and a amplified silicon photodetector. Down here is a zoom in of our sample stage. We have our sample is mounted to a dip package, and a piezoelectric crystal is mounted below the membrane. The laser is then focused using the XYZ stage on the surface of the diamond membrane. We also sample the pressure as close to the sample as we possibly can. The separation between the pressure inlet and the sample is just a couple of millimeters. The system runs with a spot size of approximately 17 microns, which is much, much smaller than the diameter of our membrane, allowing us to do mapping across the membrane with the XYZ control stage of less than a micron accuracy. And we ran it with a pressure measured in the range between atmosphere to 10 microtorr. The majority of these tests were done in the low millitorr, high microtorr range. We wanted to check our system and make sure that it was calibrated properly. To do this, we used a silicon nitride membrane that is commercially available. The membrane that was used was a square membrane of approximately 1 millimeter by 1 millimeter with a thickness of 100 nanometers. We recorded multiple resonance modes from 50 kilohertz to 2 megahertz and analyzed the first 23 modes in relation to the membrane equation based on square membranes. The square membrane equation is based on the mode number, which is N and M, the side length, A and B, stress, and density. Comparing it to this equation, we found that all of the modes fell within the expected frequency location to within 1% of the expected. We also didn't see any nonlinear Duffing behavior in the lower drive voltages for the silicon nitride membrane. Testing the diamond membrane yielded some interesting results. We swept the frequency from 50 kilohertz to 2 megahertz with drive voltages of the 0.079 millivolts to 100 millivolts. The 0.79 millivolts is the lowest that the HP3577A network analyzer can output. Shown here is that wide sweep at the 100 millivolts drive frequency, and you can see that there are many peaks up to the 700 kilohertz shown here. We looked at more than 20 peaks ranging from the first peak found at 130 kilohertz to the 1 megahertz range, and the Q factors were found to be from 2,500 to 22,000 in this range. Each peak was verified by looking at the phase shift of the peak. Shown here on the bottom right is the lowest frequency peak, which we assigned to be the fundamental mode. We based this on the fact that we did some mapping and found that the highest amplitude was roughly in the center, with decreasing amplitudes towards the edges as it's expected of the fundamental mode shape, and it was also the lowest resonance peak frequency that we could find. To analyze the results, we looked at the membrane versus the ideal circular diaphragms. This is the membrane equation. It has a mode dependence, a diameter, a stress, and a density. The important thing to note in the membrane equation is that it does not depend on the Young's modulus, only on the stress of the membrane. We also wanted to consider that due to the very high Young's modulus of the diamond, that it might act more like a plate. So in the plate equation, we have a dependence on the flexural rigidity, which is dependent on Young's modulus and thickness and Poisson's ratio. Having compared the diaphragm to both of these equations, shown on the right here, we have the black at the bottom is the membrane equation, and the red going up rapidly is the plate equation. We found that our test results fell partly in between. Though they are similar to the membrane, they definitely don't fit our membrane equation. So we looked at the mixed mode equation for a circular membrane, shown here. It is dependent on both the Young's modulus and the stress, and we found that by assuming that the Young's modulus was in the middle of the expected range at 1 terapascal, a Poisson's ratio given by the company of 0.069, a density of diamond at 3.515 grams, and an area of 1.4 millimeters, that we got a stress of approximately 129 megapascals, which is right in the range that is expected from the company. We also observed more closely each one of the peaks. Shown here on the left is one of the higher order modes with a strong Duffing. You can see as the amplitude, the input drive amplitude goes up, that you get a strong nonlinear behavior. In all of the peaks that we observed, even at the lowest drive frequency, you can see that there is a nonlinear aspect to these membranes. On the right, we show the highest quality Q factor of 22,000. And it also shows a very strong nonlinear. All of the peaks showed a strong nonlinear at the lowest drive voltages that we could measure, and the Q factors again ranged from 2,500 to 22,000. So for this work, we observed over 22 modes and found them to range from 130 kilohertz to 2 megahertz. The mode frequency shift shows a mixed mode behavior due to the high Young's modulus and relatively low stress. Using the mixed mode equation, we get an estimated estimated stress of 129 megapascals. Nonlinear duffing was observed in all of the resonance peaks that were observed, even at the lowest drive voltages, and Q factors went from 2,500 to 22,000, with the majority of the peaks showing a Q factor over 10,000. The ongoing work for this is to evaluate the diamond diaphragms in different geometries, namely square geometries and different thicknesses. Fabrication of ultra-sensitive sensors arrays due to actuation of the surface of the membrane is planned for the future after the initial testing is done. We would like to thank our colleagues for their assistance and Applied Diamond for supplying the diamond diaphragms, and also the Case Alumni Association for their support. Thank you.